Good morning, everyone. Welcome to the class Stability Aspects of Structural Steel Design, Concepts and Applications. Let's continue our discussion on Euler column theory. Previously, we studied the column with different boundary conditions. The first one is the pin-ended column. The second one is the fixed column. The third one is the fixed free column. The fourth one is the fixed and pinned column. Accordingly, we have the critical buckling load is pi square EA by L square for pin-ended. For fixed, it is 4 pi square EA by L square. For fixed free, it is going to be pi square EA by 4 L square, and fixed pin, it is pi square EA by L square into 2.046. So basically, that gives you the value of K equal to 1.0, 0.5, 2.0 and 0.7 respectively for all the boundary conditions that we have shown in the figure. So the problems solved previously had definite boundary conditions, either pinned, fixed or free. These effective length factors for definite boundary conditions can be traced back to table 11 of IS 800-2007. So if you look at table 11 of IS 800-2007, it specifies the effective length factors for definite boundary conditions. So this is the table 11, which gives you the effective length factor for prismatic compression members. So you have the boundary conditions. At one end, you have it as fixed. Basically, it means that it is restrained in both translation and rotation, the bottom end. On the other end, which is pinned, which is basically restrained in translation, but in rotation it is free. We have an effective length as 0.8 L as per the code, but theoretically we have KL equal to 0.7 L. Now let's look at the other boundary conditions, which is both fixed at the bottom as well as fixed at the top, which means that it is restrained in translation and restrained in rotation at one end, as well as restrained in translation and restrained in rotation at the other end. Basically, it is fixed at the bottom and fixed at the top. The value that is given is 0.65 L per the code, but theoretically the value is 0.5 L. So why does the K factor given in IS 800 deviates from the theoretical values? So when we have definite boundary conditions, we can have definite K values. Here we know vividly the critical load P critical and the corresponding effective length factor K for various scenarios. But in practical scenario, the columns are an integral part of the frame. So if we look at the column at the left, this is a part of the frame. What is the K factor? The bottom of the column is basically fixed, but the top of the column is unknown because it is connected to a beam and we do not know exactly what is the boundary condition at that location. So in real world scenarios, the supports are neither perfectly rigid nor perfectly free to rotate. The effective length factor K is dependent on the relative stiffness of connected members. Example, columns or beams at the two ends of the column. The plot that you see on the right hand side is known as the Woods curve. The Woods curve gives you the K values that is between 0.5 and 1.0. So the factors that are going to be helpful in determining the K values are beta 1 and beta 2. This is given at annexure B, IS 800-2007. This is for a non-sway frame. It is column effective length factor, figure 27. So you see that beta 1 and beta 2. Now what is beta? Beta is the ratio of the stiffness between the column under consideration to the total stiffness that is acting at that location based on the column stiffness as well as the beam stiffness. The K sub B represents the effective flexural stiffness of the beam and K sub C represents the effective flexural stiffness of the column. K is basically the stiffness I by L, which is the moment of inertia divided by the L. The C here represents the correction factors, which is as per IS 800, you have to follow the correction factors. But for our present studies, it is essential for you to understand that these factors lie between 0.5 fixed and simply supported 1.0. So the value of the appropriate K value between 0.5 and 1.0 depends upon the relative stiffness between the beams and the columns that is attaching to the end conditions of the column. So at the lower end, we have fixed conditions. At the upper end, we have hinged conditions. So the lowest value is 0.5 and the highest value here is 1.0. So the intermediate range is the practical scenario. Now, in order to understand this more carefully, the support condition can also be idealized using a spring stiffness to replicate the practical behavior. To analyze such columns, a more generic method of solving the differential equations used known as the Martix method. Now, previously, we understood the governing differential equations of the beam columns. We have the moment is equal to phi into EI, which is m equal to minus EI d square v by dx square. The shear is given as v equal to dm by dx minus p into dv by dx, which again when we substitute the value of m, we get v equal to d by dx of minus EI into d square v by dx square minus p into dv by dx. The load is given as q equal to minus dv by dx. Again, we can substitute the value of v here. Q equal to minus d by dx of minus EI into d square v by dx square minus p into dv by dx. This again gives rise to q equal to d square by dx square into EI into d square v by dx square plus p into d square v by dx square, which again gives you q equal to EI d power 4 v by dx power 4 plus p into d square v by dx square. So this is represented as the equilibrium equations, two numbers, and the number of unknowns are 3. The unknowns are given as v, m and small v, the displacement, which is highlighted in red color. The stress strain equation is m equal to phi into EI. The number of unknowns are 1, which is phi. The strain displacement is given as phi equal to minus d square v by dx square. The number of unknowns is 0. So we have 4 number of equations and 4 number of unknowns. So we have q equal to EI into d power 4 v by dx power 4 plus p into d square v by dx square. For columns q equal to 0, there is no lateral load that is acting. So EI into d power 4 v by dx power 4 plus p into d square v by dx square is equal to 0. So this is the governing differential equations for columns. So when we talk about governing differential equation for columns using matrix method, we need to understand few things. So q here is basically d square by dx square into EI into d square v by dx square plus p into d square v by dx square. So this again is written as d square by dx square into EI into d square v by dx square plus p into d square v by dx square equal to 0. But the previous equation holds good only it is a prismatic section. If the section is not prismatic or the moment of inertia of the section is varying along the length, we have to introduce the factor EI of x, which is given as EI into psi of x. Psi of x is the shape function. So EI is the flexural rigidity of the reference section. The d square by dx square into EI into psi of x into d square v by dx square plus p into d square v by dx square is equal to 0. So this again can be represented as d square by dx square into psi of x into d square v by dx square plus p by EI into d square v by dx square equal to 0. This is same as the previous equation, except that we are dividing this entire equation by EI. So we can substitute now this alpha square equal to p by EI in the above equation. We get psi of p double dash the whole power double dash plus alpha square v double dash is equal to 0. Double dash indicates it is differentiated twice. So the general solution for the v, the lateral displacement, takes the form v equal to c1 into psi of alpha x plus c2 into psi 2 into alpha x plus c3 into psi 3 into x by L plus c4. So there are 4 constants for which we need 4 boundary conditions to solve the above equation. Substituting 4 boundary conditions in the above equation, a of c equal to b, we have this one where the elements of A are in general transcendental functions of alpha. This begs the question, what is a transcendental function? A function that cannot be expressed as a finite combination of algebraic operations such as addition, subtraction, multiplication, division, extracting root, raising to a power. The examples of transcendental functions are log x, sin x, cos x, e power x, and any other functions containing them. So we have C equal to C1, C2, C3, C4. The vector B represents the applied loads V0 and M0. For the homogeneous case where there are no boundary loads, B equal to 0, there is no externally applied load. So A determinant of A into the vector C equal to 0. For arbitrary values of P and hence alpha, the above equation gives the trivial solution C equal to 0. When C equal to 0, it indicates that V equal to 0 of psi of alpha x plus 0 into psi 2 of alpha x plus 0 into psi 3 into x by L plus C4, which means that when the vector C is 0, all the coefficients C1, C2, C3 is 0, which indicates that V equal to 0, which is the lateral displacement. If V is 0, the column does not buckle. Therefore, for arbitrary values of p and hence alpha, the above equation gives non-trivial solution C naught equal to 0 is possible only when the determinant of the coefficient matrix A is 0. That is, the determinant of A should be equal to 0. The condition determinant of A equal to 0 corresponds to the critical load at neutral equilibrium. The column transitions from stable equilibrium to unstable equilibrium. Solving determinant of A equal to 0 is equivalent to solving an eigenvalue problem where alpha n are eigenvalues that define critical load conditions. The critical load Pn for each buckling mode is given by Pn equal to alpha n the whole square into Ei. So alpha n equal to root of Pn by Ei. Each alpha n corresponds to a specific buckling mode with higher n indicating more complex buckling shapes. Martix method solution for columns with constant Ei. Let us first solve for the critical load of Euler columns hinged at both the ends using the Martix method. So you see a column on the right side which is axially loaded with load P. The length is L, E is the Young's modulus and I is the modulus of rigidity. For constant Ei of x equal to Ei into psi of x is equal to Ei, which means that the psi of x is equal to 1, which indicates it's a prismatic cross section. So we have psi into v double dash the whole double dash plus alpha square v double dash is equal to 0, which means that v double dash the whole double dash plus alpha square v double dash is equal to 0 because psi of x equal to 1. So when we apply the load, it gets into a buckle shape and we have to find out the equilibrium at the buckle shape. The solution is v of x equal to c1 into sine of alpha x plus c2 into cos of alpha x plus c3 into x by L plus c4. When we differentiate it once, we have v dash of x equal to c1 into alpha cos alpha x minus c2 into alpha sin alpha x plus c3 by L. The constant c4 is vanished because differentiating a constant gives you 0. So when we double differentiate it, v double dash of x, cos of x becomes minus sine. So we have minus c1 alpha square sin alpha x minus c2 alpha square cos alpha x. So the boundary conditions given here are v of 0 equal to 0, which is the lateral displacement at one end is 0. Similarly, the lateral displacement at the other end, v of L is equal to 0. Since it's a simply supported condition, the moment at both the ends should be 0. So v double dash of 0 equal to 0 at one end and v double dash of L is equal to 0 at the other end. So we have 4 boundary conditions to solve for 4 constants. So when we apply the boundary condition 1, v of 0 equal to 0, we have 0 equal to c1 into sine alpha of 0 plus c2 into cos alpha of 0 plus c3 into 0 by L plus c4, which gives rise to the equation 0 equal to 0 into c1 plus 1 into c2 plus 0 into c3 plus 1 into c4. The values sine of 0 becomes 0 and hence you get this constants 0 into c1 and the another constant 0 into c3. The ones with cos actually have the value cos 0 equal to 1, so you have 1 into c2. The fourth constant does not have any coefficient, so c4 becomes 1 into c4. When you apply the second boundary conditions, v of L equal to 0, we have 0 equal to c1 into sin alpha L plus c2 into cos alpha L plus c3 into L by L plus c4, which gives rise to the equation 0 equal to sin alpha L into c1 plus cos alpha L into c2 plus 1 into c3 because L by L is 1 plus 1 into c4. Now let's apply the third boundary condition, which is v double dash equal to 0. So when we apply that, 0 equal to minus c1 into alpha square into sin alpha of 0 minus c2 into alpha square into cos alpha of 0, which gives rise to the equation 0 equal to 0 into c1 minus alpha square into c2. When we apply the fourth boundary conditions, we have v double dash of L equal to 0, which indicates 0 equal to minus c1 into alpha square sin alpha L minus c2 into alpha square cos alpha L, which gives rise to the equation 0 equal to minus alpha square sin alpha L into c1 minus alpha square cos alpha L into c2. Now we have 4 equations 1, 2, 3, 4 and we can express them in the matrix form determinant of A into C equal to 0. So when we express that, in the top line we have, the top row we have 0, 1, 0, 1. The second row we have sin alpha L cos alpha L 1, 0. The third row we have 0 minus alpha square 0, 0. And the fourth row we have minus alpha squared sin alpha L minus alpha square cos alpha L and then 0 and 0. The next one is the constant C1, C2, C3, C4 when we multiply it and then the whole thing is expressed equal to 0. So for non-trivial solution, we know that the determinant of A should be equal to 0. So when we expand this matrix, we can expand this one from the top row. So we also know that it starts with plus. The first row, first column is plus, and then it goes to the next column, it becomes minus. The third column, it becomes plus, and then the fourth column, it becomes minus. When we expand it, we have to follow the sign convention, which is something that you should have learned it from our high school. So we have the determinant A equal to plus 0 into cos alpha L 1 1 minus alpha square 0 0 minus alpha square cos alpha L 0 0. Then we have plus of minus 1 into sin alpha L 1 1 0 0 0 minus alpha square sin alpha L 0 0. The third column, when we expand it, it becomes 0 into sin alpha L cos alpha L 1 0 minus alpha square 0 minus alpha square sin alpha L minus alpha square cos alpha L 0. And then the fourth column plus of minus 1 into sin alpha L cos alpha L 1 0 minus alpha square 0 minus alpha square sin alpha L minus alpha square cos alpha L 0. So we know that the first term is 0 because 0 into something is 0. We also know that the third term is 0. Similarly, 0 into something is 0. The second term, we have minus 1 into sin alpha L 1 1 0 0 0 minus alpha square sin alpha L into 0 0. When we expand this one, we have minus 1 into the values that are given here, which again becomes 0. So the second term is also equal to 0. Finally, we are left only with the fourth term. This fourth term is minus 1 into sin alpha L cos alpha L 1 0 minus alpha square 0 minus alpha square sin alpha L minus alpha square cos alpha L 0 equal to 0. So when we expand this one, we have sin alpha L into 0 into minus alpha square, then minus of minus alpha square cos alpha L into 0. So the first term is 0. The second term is cos alpha L, which is minus cos alpha L into 0 is 0, minus of 0 into minus alpha square sin alpha L. So the second term is also 0. The third term is you have 1 into 0 into minus alpha square cos alpha L minus of minus alpha square into minus alpha square sin alpha L. So the first two terms are 0. The third one is actually the one that survives. So we have minus 1 into minus of minus alpha square sin alpha L into minus alpha square is equal to 0. So we have here minus 1 into minus alpha square into sin alpha L into alpha square. So we have alpha power 4 into sin alpha L is equal to 0. So for non-trivial solution, which is determinant A equal to 0, means that 0 equal to alpha power sin alpha L. So which means that alpha power 4 cannot be 0 because alpha is a function of the P critical, which cannot be 0. So it will give a trivial solution. Hence, sin alpha L should be equal to 0. When sin alpha L equal to 0, alpha n L equal to n pi, where n equal to 1, 2, 3, which indicates the number of buckling mode shapes. So we know that alpha n equal to root of Pn by Ei, which when substituted, we have Pn by Ei into L equal to n pi. So squaring on both sides, we have Pn equal to n square pi square Ei by L square, where P1 equal to pi square Ei by L square, which is equal to the Euler load Pe. Now substituting alpha n into L equal to n pi, in the determinant we have A equal to 0, 1, 0, 1, then sin n pi, cos n pi, 1, 1, 0, minus alpha n square, 0, 0, minus alpha n square sin n pi, minus alpha n square cos n pi, 0, 0. We know that sin n pi equal to 0. So when we reduce it, we have the determinant in the form 0, 1, 0, 1, 0, cos n pi, 1, 1, 0, minus alpha n square, 0, 0, 0, minus alpha n square, cos n pi, 0, 0. So substituting in A of C equal to 0, we have this above equation multiplied by C1, C2, C3, C4 is equal to 0, 0, 0, 0, which is the B matrix because there is no externally applied load. This gives you the equation C2 plus C4 is the first row, C2 cos n pi plus C3 plus C4 the second row, minus alpha n square into C2 the third row, minus alpha n square cos n pi into C2 is the fourth row. So we have 1, 2, 3, 4, all of the values are 0. So we can equate that. So when we equate the fourth equation, solving 4 yields you the C2 equal to 0 because alpha n square cannot be 0, so C2 has to be 0. Similarly, when we put that value in the first equation, we have C2 is already 0, C2 plus C4 equal to 0, which means that C4 should also be 0. So since we know that C2 and C4 are 0, we substitute that in the second equation. We know that we will get C3 equal to 0. So now we have C2, C3, C4 is equal to 0. Substituting in the equation Vx equal to C1 into sin alpha x plus C2 into cos alpha x plus C3 into x by L plus C4. The V of x is the lateral displacement of the column. So when we substitute it, we get Vn equal to Cn into sin alpha nx. So Vn equal to Cn into sin n pi x by L, which is the deflected mode chain. This is similar to the previously derived pin-end columns. So with this one, we have established that whether we solve the problem using matrix method or if we solve the problem using partial differential equation, we get the same result. Having established a benchmark, using this matrix method, we can solve our problems with variable boundary conditions that are represented by linear spring as well as rotational spring. Let us continue our conversation in the next class with more such problems. Thank you.